In this tutorial, you will design this board. Even if you have never designed any board before, by following this video step by step, you will learn how to draw schematic, create symbols and footprints, you will do PCB layout, and you will create 3D model of your board. You will also learn how to order PCB, how to order component soldering or board assembly, and how to order 3D printing. After you finish this video, you will use your board to build this clock, and you will learn everything important about how you can design any board and build any product you want. Enjoy this tutorial, and I really hope you will find it useful. To start, you don't need anything. No installation needed. We will use a website called EasyEDA. It's free, and we will design our board directly in internet browser. Search for EasyEDA. Click here. Register and log in. It's free. And we are going to use this Pro edition. We are not going to start from scratch, from zero. Search for this website, and as a starting point we are going to use my previous project. So search for my name, Robert Feranec, user, and click on this custom keyboard. This is going to save us a lot of time. Open in editor. And if you would like to learn how to design this custom keyboard, then I created already a step-by-step tutorial, so you can follow it. We need to save this project, and I'm going to call it clock. Okay, so this is going to be our new project. I will keep it here, save. Yes. We can close this. I'm going to refresh this, watch what's going to happen. There is the clock, see? We can close all this. And this is our project. I'm going to change names. I'm going to call this clock. Also, I'm going to rename this schematic, change it to clock, and watch what we already have. Save it. Open the first schematic page. Ta-da! I'm going to rename this. Now maybe you think, oh, but I would like to learn everything from scratch. This is also a way how you can design your boards. You don't have to always start from scratch, from zero. You can use your existing projects. Don't worry, we will cover all important things, so it's not really necessary starting from zero. I'm just double checking the title block. Everything seems to be fine. If you would like to do zoom in, zoom out, use mouse wheel and use right button to pan the page. We are going to delete this stuff. We don't really need this. And I'm going to use right-click menu very often, so you will see what kind of commands I'm using. Once you learn the shortcuts, you can of course use like delete or copy and paste. You can do Ctrl+C, Ctrl+V. Notice these selections. If you do it from left top or bottom right, there is difference. From top left, only what is inside of this selection rectangle will be selected. From bottom right, everything what is inside and what is touching the selection rectangle will be selected. I'm making everything nicer. Okay. We can delete many of these. So you can use delete on your keyboard. and we will need this, so I'm going to move it here. And maybe I'm going to move this a little bit. Okay. We don't need this. We would like to save space, so I deleted the debug header. Keep saving, okay? Don't forget to keep saving your schematic. We don't need this. There is no keyboard. I can update this. And I'm going to move this up. Okay. We are going to use melting hole, so keep this. And perfect. I'm going to add more LEDs. So these are the addressable LEDs. And we will be using them for the display segments. Be sure you correctly name everything. Okay, so these are 10 LEDs. We need more, so I'm going to copy these 10 LEDs and I'm going to paste them. Okay, we need more. Okay. Be sure you connect everything correctly. So we need to connect this here to LED 10 input. And we need to rename these. So this is going to be 11, 12, 13, 14. Theoretically, you don't need to use names here, but in PCB it is useful to see the names. When we will be doing PCB layout, it is useful to see names of these pins and nets. Okay, connect LED 20 here, and again rename these. So 21, 22, 23, and go up to 27. Delete these two. So all these are the segments for our display. This is going to be not connected, so I'm going to place this. Save. I'm going to name this. Make it look nice. Okay. I'm going to add 3 more LEDs. These are going to be used for dots. So first 2 LEDs will be the double dot, and the third one is going to show AM, PM status. Don't forget to change the net names or rename the nets. Otherwise, they will be connected to the existing nets. Remove these. And these 3 LEDs we will connect to different microcontroller pin. Okay. I'm going to copy this, and I'm going to call it dots plus external LEDs. So what we are going to do, actually, we are going to place a header here, and then in case you would like to add a few more external LEDs, you can do that. So search for LCSC website. Here are the components what we are going to use. So search for connectors, pin headers. And we are using this website because they already have symbols and footprints ready for EasyEDA. So it will be very easy to use these components in our schematic. Let's have a look what they have. This looks good. We can use it. So click here. Now copy this LCSC part number. Go back to our project, place, paste it here, search, and place into our schematic. Okay, so this is how you add new component into your schematic. You search for the component in LCSC part, and then you place it. Okay, I'm going to connect it. So to connect the external LEDs, we need 3 pins: power, ground, and the input for the LEDs. We will also use this capacitor. If a component already exists in the schematic, you can simply copy and paste it and use it. So you don't need to use LCSC then. I'm going to name this. Okay, and I'm going to change the name here. Save. The header is not going to be fitted by default, so what I'm going to do, I'm going to put this text NF not fitted text here, and I'm going to remove this from BOM, bill of material. I'm going to put here a note, so anyone who is reading this schematic, they will know why I put here this header. Okay, and save. Let's double check where this is connected. So it's connected to this level translator, and we need to connect the input of this level translator to our microcontroller. And I'm going to connect it to this GPIO 18 pin, and be sure the name is exactly same. Okay, so this way we are connecting GPIO 18 to the input of the buffer, and then it goes to the LED. We are going to do exactly same also for these other LEDs. So copy the level translator. We need this translator because LEDs are working with 5 volts, microcontroller is working with 3.3 volts. So that's why we need this component. And I'm going to copy name. I'm going to connect it here, so paste. It means now it is connected. And same here, I'm going to rename this. And we need to connect it to microcontroller. So copy this, and I'm going to connect it down here to this GPIO 28. So copy and use exactly same name. Okay, it's connected here, and then it continues to LEDs. Perfect. I'm going to update this to level translators, and we are going to connect a buzzer. I'm going to connect it here to GPIO 29. So rename this to buzzer resistor. We don't need this anymore. And we are going to place the buzzer on second page. So we need to use this port. And I'm going to name it buzzer. So always use ports if net goes to different schematic page. Okay, go on the second page, save everything. Now we are going to find the buzzer. So in audio products, we would like to use something what is kind of standard. So that's why I'm using this 9mm and passive, because you would like to have many options in case something is not in stock, like here. Maybe you could then fit different one. I'm going to update the specification. Oh, here they have more of them. Okay, but still I'm going to use this one because I know they have them in JLC, so I'm going to copy this. If they don't have it in LCSC, it doesn't mean they don't have it in JLC. Here you can see they have them. And be sure you place it correctly, okay? Plus sign is up. Let's open datasheet and let's have a look inside. So first, this is very important, maximum current. Okay, I'm going to calculate what kind of resistor we need to use. At least 100 ohms if we power up the buzzer with 5 volts. I'm going to double check what kind of manufacturer we use for resistors, and we are going to find a resistor from same manufacturer, Uniroyal, and at least 100. I'm going to use 150 ohms. Okay, so this is to limit the maximum current through buzzer. I'm going to use this big one, 600 milliwatts and 1206 footprint. Okay, we can copy it and place it into our schematic. So this is protecting our buzzer. Let's have a look what else we need there. So this is some kind of a reference schematic. We need this diode, so I'm going to find something similar in 4148. We would like to do something small like this. This looks good. So place, search. Actually it says 1N here, and here it says in, but that's okay. Place, update. Only description is different, so just confirm. See, it's just description. And place it again. And here is the diode. Be sure you place it correctly. It has to face up like this. Make it nice. Save everything. We need also transistor. They use this one, but I'm going to use something more standard. Maybe something like this. Okay, this transistor is very often used in this kind of circuits. Just remember it. Next time when you need like generic transistor, you can use exactly same one. Okay, looks good. Okay, we can copy this and place it into our schematic. Okay, save. Next, we need some resistors. Oh, we can use this one. So we need to be sure the buzzer is off. And also we would like to place a capacitor in parallel with the buzzer. In some circuits it can be useful. So we will put it here, because it depends what kind of buzzer you use. Sometimes you would like to fit the capacitor. By default we will not fit it. I'm going to copy this 5 volts and put it here. And we need port because it's connected on the page here. I'm going to copy the name of the net, buzzer, and use exactly same name also here, so you are sure it's connected together. Always when I create a net in my schematic, I copy and paste it, because sometimes by mistake you can just misspell the word, and then your schematic will be wrong because something will not be connected. So that's why I often use copy and paste for all the net names. Connect everything like this. Copy, paste, same here and also here. Okay, and as I mentioned, some of the components are not going to be fitted by default. So this capacitor I'm not going to fit by default, only if you need it, okay? If you, for example, use special buzzer, you may need it. And this one I'm not going to fit it. By default everything will be working perfectly fine. Fit the resistor only in case it's needed. Okay, name this as buzzer, make it look nice, and save. Next, we need some buttons, so I'm going to copy this circuit and I'm going to paste it here. So these are going to be like user buttons, and we can assign some features to them, but I would like to do something different, something a little bit bigger. In case we put their enclosure, then we would like to have more standard buttons. So I'm going to find them, switches, tactile switches, and let's find something what is very standard like this. These kind of switches, very often they have also different height. So as I said, in case you have enclosure, you can find some of them which are taller. That's why I would like to use different switch. Okay, maybe paste it like this. Be sure you place it correctly again. Notice how the pins 1 and 2 are connected together and 3 and 4 are connected together. Don't make mistake. And I'm going to name this user button 3, and of course we need also user button 2 and 1, so copy and paste, and one more time. Okay, so 1, 2, 3. I'm going to name this user buttons. Make it look nice. Okay. Now we need to connect them to the microcontroller. I'm going to connect them here. Okay. So copy, paste, copy, paste. You can use Ctrl+C, Ctrl+V, okay? I'm just using the right-click menu so everyone see what I'm doing. Okay, connect them correctly, okay? 13, 14, 15. Save. Here we are going to put light sensor because you know, we would like to control the brightness of the LEDs based on the ambient light. In the night, display will be a little bit dimmed. In direct sun, display has to be very bright. We can use maybe something like this. Again, this is some kind of standard sensor, so if there is problem to get it, you can always find replacement. Search for this place. Okay. So this is basically just a resistor which is changing the resistance based on the light. We are creating a divider, and the voltage between these two resistors will be changing based on the light. Okay, so I'm going to put here net name light detector, and I will put here a small capacitor. I'm going to double check the manufacturer of the capacitors which we are using and size, and we are going to use something similar. So let's select this Samsung. Maybe 15 picofarad is enough, 0402. And we can use this. Again, this is just basically space for a capacitor. If there are problems with this sensor, you can always adjust the size of the capacitor. It's important to have the footprint there. In case you need the capacitor, then you have option to fit it there. What is the exact value right now? It's not very important. make it nice. And of course add this text so everyone knows this is light sensor. Okay, I'm going to add a node. What we are going to do, we are going to place this sensor on the bottom side of our PCB together with all the other components, but it's only because I would like JLC fit the component. Once we receive the boards, assembled boards, then we will move the sensor on the top of the board. So that's what is this node about. Otherwise, you know, I would need to buy it separately and I didn't want to. Okay, I'm going to add also a node here to describe how this reset button can be used. So if you would like to update the firmware of the microcontroller, press the reset twice. I will just make this a little bit shorter, it looks nicer, and save everything. We need to connect this to microcontroller, so I'm going to connect it to this AD converter, copy and paste it here. Okay, so it's a special pin with AD converter feature. Save. Next, here we are going to place RTC, real-time clock. So first find something what we could use, what they have. I would like to use built-in oscillator. There is not really much space on the board. They have symbol and also footprint, so good. We can use this one. Search place. Put it here. And we need to connect it. So first we need to connect the power, so we will need decoupling capacitor, and power, okay, connect ground. So this is the exposed path, that's the path which is at the bottom of the chip, and this is the ground pin. We need to connect both. Now I2C bus. And for I2C, we would like to have option for these external pull-ups. I2C bus always need to have pull-ups, but our microcontroller actually it has some built-in pull-ups, but sometimes they may be too high. That's why I place these resistors here, because it's always safer to use these external pull-ups. You can always remove them if you don't want to use them, but if the I2C would not work, it's always good to have option to fit them and maybe play with specific value. Be sure you name them correctly. And now VBUT. So VBUD is connected to a battery. I'm going to use a small one, and we need this holder for the battery. I like this one because it can be directly soldered on the PCB and it's very low height. So I'm going to copy it and place it into our schematic. Press spacebar to rotate and connect the battery. I would like to connect also this output from the real-time clock. So this is going to be 1 Hertz output, which we will use in software to synchronize, for example, the dots and other things. I'm going to name this. And don't forget to save. We need to connect the I2C, so I'm going to double check pin out of our microcontroller. I would like to see where I2C pins are. Here, SDA is this one, and this is the clock. So be sure you connect it correctly, because you know, not all pins of the microcontroller can have all the features. You need to be sure you connect this I2C to the correct pins. Okay, GPIO 11. Okay, and this one is GPIO 10. Okay, perfect. And we are going to connect this 1 Hertz clock. This is not important which pin we will use because it's going to be standard GPIO. And I'm going to name this net because this is important net. This is the battery power. And also I'm going to unfit this, because when we will be manufacturing the board, we would like to only fit components which are on one side of the board or on the bottom side of the board. If we ask them to fit both, then it would be more expensive. I'm going to unfit also this, because this power LED is not really needed when you use the clock. This is more like for debugging. And I'm going to mark all these other pins as unconnected. Perfect. Now this USB connector, if we have a look on this one, it is this right angle, but I would like to use something different. I would like to use the vertical option, so I'm going to find it. Or the straight option of the connector. There are many. Maybe this one. I can use this one. There is symbol and also footprint, so this is good. And it looks good. We can copy this. And we can place it into our schematic. And this is going to be something new for you. We need to adjust the symbol, so I'm going to find the component here in libraries, and I'm going to create new one from this one. I'm going to add RF here, and we are going to customize this component. Create it together with new footprint, and here you should see it now. You would like to edit this, and I'm going to move the pins around so it's compatible with the symbol which we already have in the schematic. Just move it like this. Okay, so this is a way, if you need to customize some of the symbols, some of the components, this is exactly the way how you would do it. You can save it as your personal symbol, and then you can adjust this symbol and then use it in your project. Delete this, and I'm going to move everything back. Okay, save. Now if I go back into our schematic, I can delete this one, we don't need it. I can delete also this one, remember the name, select the one which we created and place it. Okay, and you can see we can easily place it here. These are unconnected. And don't forget to put back the name reference designator. Perfect. We are going to run DRC check to see if there are no errors. Let's have a look. Oh, these are not connected because we deleted the debug connector. And what is this? I'm going to add reference designator. Perfect. The other warnings, you can just ignore them. These warnings, you can ignore them. That's fine. No other errors, no other warnings. Save everything. Let's go to PCB. And first we are going to delete all 3D stuff. That's the enclosure, the box for keyboard. But it looks like these layers, they are locked. So we need to unlock everything first. Now let's try to select them. Okay, press delete. Enable all the layers. And we are going to keep this, the components around the microcontroller and microcontroller itself. So select all these. And yeah, delete everything. Also delete these and these. I would like to keep the routing and placement around the microcontroller because that's the most difficult one, most time-consuming one. So I don't want to do it again. And this means it is going to help us to speed up the layout process a little bit. If you would like to know how to do it from scratch, again, you can go back to my keyboard tutorial, and you can follow the keyboard tutorial to do the microcontroller placement and all the components around the microcontroller. You can do it by yourself. Okay, now import all the changes in the schematic into our PCB. Keep this checked. Okay, now we have all the components from our schematic in PCB. Before we start, we are going to change all the 6 mil tracks to be 8 mils. So be sure we are working with tracks with 6 mils. Find all. This is how it should look, and just change them all to 8 mils. Later I will explain why, but during whole design, during whole PCB layout, we are going to work with 8 mils for standard digital tracks. Let's have a look on 3D model. So right now, this is not exactly our board, but don't worry, we will adjust this. Just double check 3D models of the components if they are okay. And we can start working on the layout. So be sure you are using mils. We are going to work with components. And first we are going to place the mounting holes. Okay? Be sure we are working with mounting holes. Place the first one here. So you can directly write the X and Y position. Or you can also move them by cursor, but do it the same way as I'm doing them, so you have the mounting holes exactly at the same position as I will have them. Okay, so this one, move it up, and the last one, double check the name or reference designator of the mounting hole and change the position. Okay, save. Now we are going to draw the board outline. So we are going to draw the shape of our board. Do it like this, okay? Use exactly same position and same width and height. Okay, we would like to have rounded corners so it looks nicer. Disable filter, enable only working with components, and have a look. Okay, so this is much better. This is going to be our PCB, and we have to place there all the components which are outside of the board. Okay. So let's move this a little bit down. Watch what I'm going to do. So select everything. Unlock. And just move it. Watch the position of my cursor, okay? I'm holding everything here in the middle of the path, and watch the position of my cursor. Okay, now select just the microcontroller, and you should have this position of your microcontroller. Then you will have everything in the same place as I have it now. I can lock it back, and we can also lock the mounting holes so we don't move them by accident. Now I'm going to move everything on bottom layer all the components, most of the components will be on the bottom layer, and set the grid size to 100 mils. We are going to place the LEDs. First I'm going to move them a little bit closer, and be sure you are moving them in the order, okay? From LED 201. Watch where I'm going to place it. Use exactly same position. And also the rotation. We are using a very big grid, so it should be also easy for you to place these LEDs, because they basically jump into right position. And now you can see how we are creating the first number of our display. So these are the 7 segments. Be sure they're ordered correctly. Okay. Double check 3D view, and this is how it looks. Okay. We can do the second number. So again, I'm going to move everything a little bit closer. Follow the numbers. The LEDs, they have to be ordered in order, otherwise segments will not be correctly shown when we will be writing firmware. And again, place them exactly into same position. Okay, so LED 200, 8, 9, 10, 11, 12, 13, 14. Perfect. Double check everything. Okay. Let's continue. It's almost done. It's very quick. Okay. So 15, 16, 17, 18, 19, 20, 21, and double checking. Perfect. And last 7 segments for the last number. Okay. Place everything. Be sure the rotation is correct, because then it will be easier to connect the pins. Double check the order. Perfect. Now the dots, so 2 in the middle and 1 here. Be sure you use exactly same position and rotation. Okay, we can have a look. So this is our display. Save everything. Now these capacitors, decoupling capacitors, we need to place them. So we would like to work with symbols only. I'm going to select all of them. All decoupling capacitors for the LEDs. These are the capacitors. I'm going to move them a little bit closer so it's easier to work with it. Oops. Okay. And now we are going to place them. So again, first I do this preliminary placement so I know which one goes where. Oops. Do it also for the other number. And third number. It is a little bit time consuming, but it's super easy to do this. Almost ready for the placement. Okay, zoom in and watch where we would like to place it. We need to place them close to the power pins. So what I'm going to do, I'm going to find the power here and I'm going to change the color. We can use orange. Now you can very nicely see all the pins which are connected to power. Again, we would like to continue working with components. Be sure you are using same grid. And we are going to continue with placement. So this capacitor, place it down here. And notice how I rotated the capacitor, okay? The power pins, they should be close to each other. So again, rotate, press spacebar, you can rotate the components. Do it exactly same way as I do it. Place them at exactly same places. And use same rotation. It will make the layout for you easier because then you can easily follow this tutorial. Okay, half is done. The second half. We are doing it exactly same way because then we can easily also copy and paste the layout, which we will be doing around these LEDs. And it will help us to save some time when doing PCB layout. So we don't have to draw everything. We can simply copy and paste a lot of tracks and a lot of connections when everything is placed same way. You will see later what I mean. Now the capacitors for these LEDs, here they are. So this one will go here, this one here, this one here. And I would like to hide these reference designators because they are kind of disturbing. So select all these components, watch what's going to happen, okay? We disabled them. And also we would like to lock all these LEDs, so by accident we don't move them. Now the buttons, we need to know which one is which one, so button 2, place it here, use same position, same rotation, okay. Now button 1, okay, rotation 90, and the last one, perfect. I'm going to update this. By the way, the yellow crosses, which you can see there, they mean error, but you can ignore them for now. These buttons, so reset first, place it here, and this one you can place it here, okay. Now the USB connector, and you can see there are also these errors, but again ignore them for now. Now the buzzer, light sensor, what else? Regulator, 3.3 volt regulator, this is the RTC. Now the battery, this is going to be on top layer. It's one of few components on the top layer, or basically it's only one component, but later we will solder the light sensor on the top, as I mentioned when we were drawing the schematic. So right now it looks like this. You can see the light sensor is right now at the bottom, but then we will place it on the top. Again, I'm going to explain why, because when we will be ordering the PCBs, then we can order only assembly of the bottom layer, and it's going to be cheaper. If we order assembly of 2 layers, it's going to be more expensive. We are going to place the components around the buttons. Be sure you have same grid size. You can see where these components are connected, okay? Watch the lines. And when you hover cursor over the path, you can also see which paths are connected together. Components around the second button. I'm going to use smaller grid because with smaller components it's harder to place them close to other components if you are using very big grid. So this is the position. Place this capacitor. Okay, and this resistor between them. Again, hover cursor to see which paths are connected together. Hover cursor over a path. And then you will see where it is connected. Now, components around the USB connector. So these are the ESD diodes. They need to be placed close to the pins. Second one, watch the lines, you can see where they are connected. Okay. Now these resistors. This one goes down here. So place it maybe like this. The second one goes on the other side. ESD close to one power pin. Then capacitor close to power pin behind the ESD. I'm going to delete this, also this. Second ESD on power. Maybe like this, okay. And capacitor. Double check where everything is connected. Okay. Now components around this LDO. So first this output capacitor. It needs to be close to the output pin. And the input capacitor needs to be close to the input pin. Power for LEDs. It needs to be somewhere here because it's basically from the USB power. And here is capacitor for the LED power. I really would like to hide all the designators because it's very disturbing. So watch what's going to happen. They are going to disappear. Perfect. Let's continue. Now the header. So this is the header for the external LEDs. We are not going to fit it. If you like, you can even like solder wires there directly. You don't even need to use connector. And there is also these capacitors which need to be placed close to the header. Okay. Components around the buzzer. So first the diode. Maybe like this. Now the capacitor here. Transistor. Watch where it is connected. Don't place it too close to the hole for the LED, because then they may have problem to manufacture the PCB. And this one goes here. And this one, we can place it somewhere here. Okay, change the grid back to 10 mils. Now the components around the light sensor. So first the capacitor. We can place it, for example, here. The resistor. This one is tricky because you can see it's connected to 3.3 volts. So maybe we need to place it somewhere down here. I will make some space. Delete this. And place it maybe like this. Okay. Now the components around the RTC. I'm going to move it a little bit because it's too close to the switch. The coupling capacitor. We can delete this. Pull up for I2C. We can place it also here close to the microcontroller, it's fine. Because here is some space. Second one. Again, maybe we can place it close to the microcontroller. Okay. What else is missing? going to clean these, they are not connected. We need some space. So I'm going to move this. Also this one. So this is the reset circuit. You can see where it is connected when I hover cursor over the path. It goes to the push button, see? Okay. Now the level translators is connected to the first LED. So I'm going to place it here close to the first LED together with decoupling capacitor. Now the second level translator, this one is connected to the dots. So I'm going to place it here. Maybe rotate. And also we need the decoupling capacitor. Place it close to the power pin. Okay. Maybe we need to move this little bit, so I'm going to clean it. Okay. And maybe move this a little bit. Okay. And also this flash memory. Move it like here. Okay, double check the position. Here is the final position of the flash memory. I can delete this. You need to click twice if you would like to only delete one segment. So, but not double click, but click once and then second time. This is the decoupling capacitor for the flash. This one is also connected down here. So we need to place this. Maybe somewhere here. And this one. Here it is. Okay. Power LED. We can place it close to the power. This one is not going to be fitted. As I said before, maybe when you are debugging the board, it may be useful, but for the final product, for the final clock, it can be a little bit disturbing. We don't need to fit it because it would, always be green and always on. Okay, what is this? Oh, it's close to this button. Which one is it? This one? Okay, so we need to place this resistor close to the button. Be careful, do not place it too close to the cutout for the LED. Place also the capacitor. Okay, and the second resistor. Double check where everything is connected. We can clean this a little bit. What is this? Oh, that's the bigger capacitor, which we would like to have somewhere close to the microcontroller area. Maybe we can place it somewhere here. Okay. And the last component, which one is this? Oh, it's the buzzer resistor. So we can place it maybe here. This is series termination resistor. It should be close to the microcontroller, close to the output. Okay. So we place all the components, and I'm going to clean the unconnected tracks. Okay, looks good. On the top we can still clean this and this. And we can also delete this. That's a big polygon. We will draw it later. Okay. And I'm just checking if there are no other unconnected tracks or vias left. Good. We can start doing layout, and we will start with these LEDs. So we would like to work with vias and tracks. Be sure grid size is 10 mils, and we are working on bottom layer. This is how you draw tracks. So just left click and then press Tab to change the width of the track to 20 mils. And then left click, you can double check the width, you can double check the length, and then we can place via. So via makes the connection between layers in PCB. This is the size 2412. Be sure we are using exactly same size for vias. I'm going to copy this, pick it up where the path is, and place it also on the other pins. Do it like this. And now we can copy this, pick it up again where the pin is, and place it on all the other LEDs. So this is going to help us to speed up the layout process. We will do same also for these capacitors. And once we finish all these for this first number, then we will be able to copy and paste it also on all the other numbers, because the placement is same. So we are going to do this only for this first number. And also what we can do, we can connect the LEDs. So zoom in and let's have a look how they are connected. And this is how we draw the connection. Press tab to change the width to 8 mils. So this is going to be standard width for digital tracks, and connect the pins. Now connect these two. Always hover cursor over a pad and you will see where it is connected. Okay, you can see where it is connected. If the bending of the track is not what you are expecting, try to use spacebar. Okay, spacebar will change the angle of the bending when you are doing layout, when you are routing tracks. If you would like to move it, just hover cursor over the segment of the track which you would like to move, press left click, hold it down and just move it. Okay, go around the vias. And also make connection down here. Okay. I'm just double checking if everything is connected correctly and nice. Maybe I will adjust this a little bit. Now let's work with vias and tracks. We are going to select all these connections what we just created, pick it up in one of the pins or one of the paths, and now place it on the exactly same path, but the second number, third number, and fourth number. So this was really super useful. Okay, if you can copy layout, then you can do it this way. Before we continue, I would like to mention that if you would like to learn more about electronics and how to design boards, check out our online courses. You will find everything important there, from basic board design up to advanced board design and high-speed PCB layout. We have courses in Altium, Cadence, KiCad, and also courses covering many different topics, for example, FPGA, EMC, measurements, and so on. Visit our website at fedevel.com. Now, let's go back to layout. Now this flash, we are going to connect it on top layer and press Shift S. You can change the view. So you try Shift S and you will see now this second layer is grayed out. But if you do it Shift S again, then it will completely disappear and only one of the layers will be visible. And then press Shift S again, you will see all the layers. Just connect all these vias. This is not very difficult. Keep space between the tracks. Okay. Now go around. Connect also this. clock. And we need a via here, so I will go a little bit down. And connect it. Connect the ground pin on the bottom. Use 20 mils for power tracks. Okay, and the last one. Don't forget change the width back to 8. 8 mils for digital tracks. And draw the connection. I'm just double checking. Save. Now this continues. Oops. Why it doesn't show anything? Okay. Okay. So let's connect these. Continue down here, connect power, so make this wider, 20 mils, and put there a via. And connect the switch or button. Go around these components. Okay. Now, powers. And we can also connect all these ground pins. So it's always very useful when you are doing layout. Put there all the vias before you actually start drawing signal tracks. It's very helpful because then you will know where you need vias and you can go around them. If you would route signal tracks first, and then if you would be placing vias, then you may need to reroute many existing tracks. So always place vias first, and then do the layout, then connect the signals. Okay. Now this USB, but this is a special signal because it's USB signal differential pair. So I'm going to select here follow rule, and now watch the thickness. Thickness is going to be set based on the rule 6.1 mil. Later I will show you where the rule is set. You will see. Now connected also here. So this is not the most optimum layout for USB signals because these are differential pairs. They should be just routed together. There should be no stops or pieces of track which are going basically nowhere. But there is no other way how to route this connector. So that's why we have to do it this way. Now let's connect this resistor. Okay, go around. Perfect. And also on the other side. Also this ground is missing. And this looks good. For power, again, use 20 mils. So this is the main 5-volt USB power. And same from this other pin. There are 2 pins for power from this connector. And we can connect it also here to the resistor for powers for LEDs. Don't forget to save. Next here. So let's have a look. We may need to move this a little bit. When you are placing these decoupling capacitors, they always should be as close as possible to power pins. But as you can see, we don't really have much space here, so I had to move it a little bit further from the power pin. And let's connect it. So this time I'm using a track with 8.1 mil. Okay, because notice this, okay, it's very important, because the path from the microcontroller is very small, so I had to use thinner trays. But I didn't want to use 8 mils because by the end of the design we will be changing all 8 mil tracks back to 6 mils, and I don't want to change the width of power tracks. That's why I use 8.1 mil. Here we are going to place vias. We will need some space for vias for the other tracks, especially for the clock signal. And let's route this I2C. Don't place the component very close to the edge of the board. It can cause problems during manufacturing. So leave some space. Same for tracks, okay? Do not go to the edge of the board. Leave some space between the edge of the board and the track. Make it nicer. Okay. Now this battery. Again, it's power, but we need to make it not bigger than the path. Place a via. And here is also, no, I'm going to double check. So this is what is the width? 13. So I'm going to change this. Okay. Now the ground pin. Again, use 13 mils. So the track is not wider than the path. Here is a ground pin. So connect it. And also connect the power. this is going to be quite busy, so I'm going to place the via somewhere here. Okay. Now this place is tricky. We can't really put there any vias or tracks because there will be battery at the top. So we have to go away from these pins. And same here, okay? Go away, do not place vias where the battery is. And I place one ground via to connect the ground path for the battery. Now let's connect this battery voltage. I would like to make it as wide as possible. But again, we need to go around the battery. And it's not really necessary to connect both these paths. One would be okay, but we can do it, why not? Okay, let's go back on bottom. We can connect also this capacitor. So this is the bigger capacitor, which is placed close to the microcontroller. Oh, there is error. I'm going to move it a little bit. Always when you see the cross, yellow cross, it means there is error, violation, rule violation. The rules are actually preset from the original project, so we haven't talked about rules yet. You can just use exactly same rules which I use for the original keyboard project, because this PCB will be manufactured by same PCB manufacturer, JLC or JLC PCB. Okay, save. I'm going to place here special region, so I don't forget there should not be any copper. Okay, so this is basically the area where the battery will be located. And double check if there are no vias inside of this area and no tracks. I'm going to move this a little bit away. Okay, let's go back to bottom. Clock here. So not much space, but we will try to place a via here. On the top I'm going to adjust this a little bit so there is no short circuit. And let's continue. So this is going to be the 1 Hz signal coming from the real-time clock. And it is very precise. It's more precise than running the clock directly just from the microcontroller. That's why I decided to route this 1 Hz signal. Because this RTC, it has some kind of compensations, and you know, it's very, very precise. If you don't use RTC chip, dedicated chip, you still can do some RTC clock also from the microcontroller, but after some time the clock may be you know, may not show the correct time, because it may shift a little bit more than if you are using dedicated RTC chip. I'm going to connect the second line from the I2C bus. Okay, so this is the clock. What else? We need to connect buttons and where it goes. We need to swap them. These two, we need to swap them. So I go to schematic, and now watch. If you need to make some changes in schematic, so this is how you do it. I'm going to copy this, and I'm going to put the button 3 down here and button 1 here. So I changed the schematic. Now you need to update your PCB, so go to design, update PCB, and watch what's going to happen, okay? Watch down here, they are going to be swapped. So it's easier to route them. Here, watch. Okay. See? Now it's easier. Perfect. We don't need to cross the tracks. So let's continue with layout. Keep some space between the tracks. Now, because we are routing on bottom layer, we can go under the battery. We just can't use the top layer under battery, okay? We can route on the bottom, it's fine. And we can't place vias there, because vias will be visible also on the top. Okay. Second button. Let's go up and connect this. Okay. There is no space here, so we need to move this a little bit. First I have to move this, but there is no space again. So let's reroute this a little bit. Okay, now we can move it. We can move also this and this, and now we can move the via. Let's see if there is enough space. Perfect. Okay. Connect these resistors and capacitor. Keep space, okay, keep space. I'm making it nicer and spreading the tracks. So this is clock, okay? We would like to have it maybe a little bit further from the other tracks, especially if there is space. This is also a clock, so I'm going to move it a little bit away. Okay. Okay. Press Shift S. You can only see the one layer. Shift S, Shift S. Okay. Reset. Here is the reset, so I'm going to connect again the resistors and capacitor, and then the push button. But this one goes up, so I will connect this on top layer. There are a couple of tracks which will need to go on the bottom layer, so I'm going to move this on the top, and then I will go back to bottom. I will redo this one a little bit later. I just need space for this via. Okay. Again, this is something, if you don't have space, if you have like very limited space, then on these switches you don't really need to connect these two pins because they are connected inside of the switch. But we have a lot of space, so we can connect both pins. Now I'm going to redo this ground layout here for the capacitors. Okay. Also here, maybe move it a little bit so there is no error, there is no violation. Okay. Connect this. So each power pin, ideally you would like to connect each power pin to at least one via. So that's why I don't connect all the power pins on the top together. Here you can see I could connect them together, but I wanted each capacitor have their own via. Many people ask actually about this, why I just don't connect all the ground pins together and then use one via. That's not the recommended way to do it. Okay, for power pins, ideally at least one via per power pin. For higher currents you may need to use more vias, multiple vias. Okay, we can connect this, but we will need to change layers. So go up, maybe move this a little bit. And connect the buffer or level translator. Okay. Now this decoupling capacitor. Okay. And connect these together. Because this decoupling capacitor, it belongs to the pin, so that's why I use one via for the capacitor and the power pin of the level translator, because the capacitor is there for the level translator. And connect the output to the first LED. Now let's finish connection around this switch. And power here. I'm going to copy this and I'm going to place it also here and here. You can place it also here. And finish also this. Okay. This was easy. Same here. And we still need to connect the ground pins or ground paths. Maybe here there is space. I don't like this. I didn't like it because it was bending. I could make it straight because I would like to copy and paste it also on these other parts. Okay. Let's continue here. So what else we need to connect? Here. Where this goes? It goes to the light sensor. So let's go up. This is actually analog signal, but we still can use 8 mils. It's fine. We can't really make it much wider. Very often I use wider tracks for analog signals, but you know, this one is it's not like super important signal. It's not super sensitive signal or anything. So we don't really need to worry. I'm checking if there is enough space because we need to go down also with this track for the second level translator. So I'm making some space here. Okay, we can connect it now. Keep space between tracks so they don't influence each other. See, they're away. We can connect all the other pins around this level translator. So first this decoupling capacitor, okay. Now the power pin, okay. Okay, and output goes to the LED, first LED for the dots. What is next? This buzzer. So we are going to connect resistor for buzzer. I'm going to move this a little bit because sometimes PC manufacturers, they don't like the sharp angles, so that's why I move the track. So it just goes directly from the corner. Okay, let's go on the other side or other part of our PCB where the buzzer is located. So this is a long track. Go around like this. Use backspace on your keyboard if you would like to go one step back. So if you click and it's a wrong click, you can use backspace. Okay. We can connect this now. So I did direct connection with the diode. And now I will go down here. So this may be a little bit unusual routing. Notice I could connect it directly here, but I went here to the diode and then down because the diode is there for some kind of protection and we don't want the signal spread to rest of the PCB. So we would like to have the diode in the way how signal travels. That's why I routed the tracks this way. So basically the diode will help to filter the possible noise when it is in the way of the signal. At least that's how I imagine this. Connect the rest of the pins. Okay, I'm going to connect these dot LEDs. Also here. We can connect the connector or header. Okay. Also ground. We don't need vias here because these are through hole pins, through hole paths, so they are connected on all layers. I mentioned this because I know maybe some people who are starting with PCB layout, they may think they need to place vias there, but no, they don't. If there are through hole pins, you don't need to use vias. Okay, this is also long track. We need to connect it to dot LED. Okay. I'm just trying to make as much space as possible between the tracks. Because, you know, signal traveling through one track, if they are routed very close to each other, then this signal can create noise on track which is routed very close. If we spread the tracks, if there is a big distance between the tracks, then the noise will be much lower, or there will be no noise picked up by the neighbor tracks. Okay, we can connect also this. So this is the connection between the first number connecting the second number on our display. And here we need to connect third number to the fourth number. Okay. Again, making a lot of space around the tracks and also making it nicer. You know, these are the layers which are visible. Top and bottom layers are visible, so anyone can see these layers. Now I'm going to connect this USB. Again, routing based on rules, okay? Let's go up and place vias here because we need to go on top layer. I copy this. Now you can use X and Y to flip, okay? On your keyboard, press X or Y. You will see what it does when you are copying or placing something. Continue on top layer. And connect this. I'm going to connect it like this. Perfect. Looks good. What else? I will put it back. Okay. Now this regulator, right now we will just draw all the connections, but later we will do polygons. So polygons, it means it's like copper area. Polygons are not like tracks what we are drawing right now, but I usually draw all the polygons by the end of the layout. Right now we just would like to connect everything. And I placed 4 vias here because this is a power, and for power very often you would like to use multiple vias. Okay, even if the current is not so high, there is a limitation on how much current one via can handle. And in this case it's definitely more than current going out from this LDO, but it's very good practice to use multiple vias for powers. So learn this habit. Here is how we will draw the polygon later. You will see. And because we have multiple vias on power, we need to place multiple vias also on ground. There will be actually many vias here for the ground, because we will use it also as a method to cool down this regulator. Because this is LDO, it can get hot or warm if current is a little bit higher, and you need to take this heat away. So one of the ways how to take heat away from regulators or from components is to put there multiple ground vias in case you have big solid ground plane somewhere in your PCB. It will spread the heat through the ground plane. See, because there is not like much space here, so we can't really draw big ground plane on this bottom layer. So that's why we place there multiple vias, and we will use the big ground plane which is in the middle of the PCB. We didn't speak about this, so this is how we draw the polygon later. We didn't speak about the inner layers of this PCB, but I will explain later. This is actually 4-layer PCB. Inside of the PCB there are 2 solid ground planes. Later I will show you how it is set up. Finish the connection of this power supply. We also need the ground via here. Okay. And we need to continue from here. And connect a couple of other things. So notice I routed the how I routed this because I wanted to have direct connection between the input capacitor and the LDO. That's why it is routed separately. I need space. We need 5 volts for buzzer. Okay. Perfect. Maybe move this a little bit. And I would like to see what else is not connected. So I would like to show these lines which are telling me what connections are missing. So from here we can go on top layer and we need to connect the level translators. So here is one level translator. They are powered by 5 volts because they are connected to LEDs. LEDs are powered from 5 volts. Okay. We need to go up here. Okay. Here we can move this a little bit. It doesn't want to move. I will redraw it. So again, if you would like to only delete segment, one segment, then click and then click again. First click will select the whole track, but the second click will only select the one segment. So these are the inner layers, see? Ground planes. But it looks like it's kind of broken after the import. So I go to Layer Manager and I'm double checking. So it's set as a plane. Layer 2 is plane and layer 3 is plane. Apply. Okay, it's back. So now select the plane and double check if it's connected to ground. Okay, and rebuild the plane. Also on layer 3, ground, rebuild. And now all the ground vias should be connected, and basically all the ground pins are now connected. Let's continue with this power for LEDs. I'm going to use multiple vias. Oops. Again, later we will draw big polygon. Right now we will just try to connect everything. This is how I usually do layout. So in the first stage of layout, I just focus on connect everything. And once you connect everything, then you can do some kind of optimization, because then you will see where you have some space. And then by the end of the layout, I draw the polygons, because sometimes it's very hard to see through polygons and planes. So that's why I do it at the end. But I'm going to connect everything because when we run DRC, we would like to be sure that it is possible to connect all the pins in your PCB. So that's why I just draw this connection. So a little bit later we can run the DRC check just to confirm we connected everything. DRC, it means design rule check. Okay. Almost finished. So these are the dots. And now the first two numbers. Okay. Go down here. Okay. And the last one. Okay, perfect. So there is no orange line right now. What else is missing? What is not connected? Purple lines, 3.3 volt. Okay. Also here. Oh, this is big one. Okay. Too big. Perfect. Few more. And we need to go up where the buttons are. Be careful, okay? Do not go into the area where the battery will be. Okay. Okay. And again, later we will draw big polygon, big copper area for this 3.3 volt power. Right now we just would like to see if we can connect everything. LED. So this is the resistor for LED, power LED. Okay. Save. Here is something. So this is the connection between the second number and third number. And we will need to go on top layer. So go on top layer. and maybe move this little bit. Okay. And then we need to go back on bottom and connect it here. Perfect. What else? These ground pins or ground paths. These are easy because ground is everywhere. Move it away, like this. I will correct this again, because there was the sharp angle. This is the sharp angle, see? That's what PC manufacturers sometimes, they don't like it. So I move it like this. Because they call it like acid trap. So when they are etching PCB, acid can be trapped in these sharp angles, and maybe later it can cause problems. Or maybe even during PC manufacturing it can cause problems. Okay. What else is missing? I will move it here. Go and run DRC. We will see if we connected everything. Here, connection errors. So we didn't connect this. What is it? Oh, this is the LED. So if you are not sure if you connected everything, you can just run this DRC check and it will tell you. You can very easily find the missing connections. This is weird because this is unconnected ground. We need to connect this RTC exposed path. So I'm going to do this. Okay, and this it's the same error. And this one, I forgot. Ground connection here. I will make this a little bit wider. Okay. So rerun DRC check. I will show you how to fix this. There are actually a number of errors connected with ground planes, which are inside of our PCB. Most of these yellow marks, which you can see here, they are connected with not updated ground planes. So go on ground plane and notice we need to create space around these vias and we have to remove this. It's called island. So keep islands, no, and now see what happened. So the plane was rebuilt, refreshed, and also all the new vias, now they have space around them. So everything is okay, but here is something. I need to rebuild also this one. Okay, perfect. But here there is still some kind of Error. What's the problem here? I don't know. Let's maybe rerun DRC. Oh, it's something with differential pairs. Oh, I understand now. Okay. So we have to adjust the length. So as I promised, I'm going to show you where is the rule for differential pairs. So here are all the rules. These are the rules for differential pairs. And we need to increase this tolerance to 25. This should fix the error. It's gone. Perfect. Cool. Save. We are going to draw the polygons. So place, copper region, polygon. So these are the copper areas. And usually you use them for powers. So I'm going to draw it like this. Around the connection for LED power. You can draw it exactly same way. I don't go exactly to the edges. Okay. Now, be sure it's connected to the LED power. So do it like this and confirm. So this is polygon, okay? This is basically power plane for the LED power. I'm going to move this. Okay, so it doesn't go out of the power plane. Now here, we would like to place something what is called stitching vias. So in all the places where signals are changing layers, you need to be careful, and sometimes you need to place there these ground vias, especially in the cases when they are changing reference planes. If you would like to learn more about reference planes, I created a number of videos on this topic, so you can watch them and you will understand why we are placing these stitching vias or ground vias here. It is basically to control how signals will flow through your PCB, especially return currents. I'm going to continue with the polygons. So we are going to draw it for this 3.3 volt power. Go around all the 3.3 volt pins like this. Okay, almost finished. Maybe like this. Okay, and connect it. Again, be sure it's connected to 3.3 volts. Confirm. Maybe we can make some adjustments. So make adjustment, just select the polygon like this, and then you can move the edges like this. Okay, you always need to then rebuild the polygon if you make some changes. Few more adjustments here. I will keep it like this. Maybe move it. I don't like it. And this is something what I don't want to have there. So edit, polygon, and now we can reshape the polygon. This is very useful because sometimes it's very difficult to draw these big polygons, so you need to know how to edit them. Okay. I move this little bit. I will move this. Next here. So I'm going to draw like very small polygon. And I'm doing this especially because I would like to show you something. You can specify order how these polygons are created. So if you go to Tools, Copper Manager, Priority, and we would like to move this up. So this one is done first. Okay. So rebuild, and now rebuild this one. Okay. So priority is very important. It will basically tell the software which polygon is more important, which polygon they should, or the software should draw as the first one. I don't like this. So there is mask under battery, and we don't want to have it. So what I'm going to do, I'm going to remove the mask. So I'm going to draw on the mask layer, and I'm going to remove the mask because, you know, mask has some thickness. And from my past experience, if we keep mask there, then the contact between the battery and the pad may be affected. So that's why it's very useful to remove the mask for this component. Okay. Here we need small polygon, so I'm going to draw it. So this is the connection around the LDO. Perfect. 3.3, confirm. Now also the ground polygon. Okay. Okay, Perfect. Also here. Confirm. And here. Save. Next we are going to add logo here. So I'm going to place image. This is our logo. It is just black and white picture. And I'm going to set the size and place it here on PCB. I'm going to move it to bottom solder mask layer. And it's because I would like to make the logo look gold. So basically, where the logo is, we are going to remove the blue color, the blue mask. And that's only first step. In the second step, we need to draw polygon or copper in this area. So then when they do gold plating, then the area without the mask will be gold. So the logo will be gold. Okay, so we have the mask, and we still need to draw the polygon. Because if we don't draw this polygon, then the logo will not be gold. We will only see the basically prepreg or of the epoxy layer of the PCB. I'm also connecting the logo to ground. We don't want to have a piece of copper unconnected. So I'm not connecting the logo to ground, but I'm connecting the copper under the logo to ground, so it's not left unconnected. But right now you can see these wires are connected to LED power, so I'm going to change it to ground. Okay, now it's okay. Perfect. I will adjust this so it looks nice. Okay. Okay. I'm just moving it a little bit so it looks nice. Okay. And we can double check this. So here is the logo. See how it's going to look? Nice. Perfect. Save everything. I'm going to search for JLC PCB capabilities, and we would like to know how small text we can use on PCB. So on bottom cell screen layer, we are going to put some information. We are going to mark the buttons, and I'm going to change the view to this flip view because we would like to see the PCB from the bottom, like we would be holding the PCB in our hand. So that's why I flipped the view, otherwise you would not be able to read the text which is on the bottom. And So this is the user 1 button. Okay, so I'm going to move this text down here. Okay, so this is user 1. I'm going to copy it. Next one is this. So this is user 3. This one is going to be user 2, user 2. Okay, perfect. Next, we would like to put maybe some text here. So this is the light sensor. Forty is the smallest, so I could make it smaller, but it looks like it fits here. So I can leave it. Okay. Then boot button and reset button. So this one is boot. Always place this kind of text on your board so people can use your board also without checking schematic or reading manual. So this is the header for external LEDs. And I'm going to place more information here on how the pins are connected. So signal, ground, power. Okay, perfect. We can save everything. Double check how it looks. Nice. Flip the board back so we can read the text on the top layer. We are going to put here some information. So first the board name and the version of the board. Very important, because sometimes happen you have multiple versions of your board. You need to know which one is the one which you are holding in your hand, because some of the versions may be very similar and you need to know you are working with the latest one. And also copyright, so you can put here your company name or your name if you designed this board by yourself. Okay. I'm going to update this version also here, because by default I think EasyEDA use the version 1.0 and I use or version 1 issue 1. That's what it actually means, V1 E1. And also I would like to put advertisement on our online courses here. So if someone would like to learn more about electronics and how to design boards, don't forget to check out our online courses, okay? So learn how to design boards. I'm going to center this. I'm going to copy it, paste, FEDEVEL online courses, make it a little bit bigger so everyone can see it. Again, you can put here information about your company, or maybe about what you do, or about your project. It's really up to you. And don't forget to visit our website. Make it even bigger so everyone can see it. Perfect. I love it. I'm just kidding. You know, I have to do this because some people think free YouTube tutorials are really free, but I spend a lot of time actually preparing this tutorial, and it costs some money to create these boards, so that's why I put that advertisement. I don't like this here, so I'm going to actually delete this mask removal, what we did before, and what we will do, we will update the whole footprint, because that's the proper way how to do it. So I'm going to find this component. Do you remember how to update components, how to create your own components? Search for them in libraries. Now create your own, so save this into your personal libraries. We will create also a new footprint. Now edit, I don't see it, here it is, okay, edit this component or this footprint. I'm going to delete this shape, okay, and I'm going to draw it again. So I will draw it as a circle, so we know where exactly the battery is going to be. And of course we don't want to draw through the path, so I'm going to draw the cell screen as arcs. Spacebar to rotate, okay. Now we need to know from what direction we are inserting the battery. So basically where is the front of this footprint, so it's very important to mark it. So this arrow is actually showing direction how the battery is inserted, or where the battery is inserted from. And I'm going to draw also the I'm going to remove the mask in the area where the battery is going to be placed. So this is the proper way to do it, because you know, if you do it directly in PCB, then you move the footprint, and you need to move this unmasked area together with the footprint. So that's why it should be inside of the footprint. So place this new component into our schematic. delete the old one and put there the new one. Update PCB. So watch what's going to happen. I'm going to remember first what is the position. I'm going to save everything and update. So it's going to remove the old footprint and it's going to put there the new one. So we need to place it back like this. Double check the position and rotation. Perfect. So this is much better. I can immediately see where the battery will be, and you know, we automatically also remove the seal screen in the area where the battery will be. I'm going to put here text information about the battery. Again, something very useful, so everyone knows when they need to replace the battery, and if there is no battery, then they know which one they should buy. There is just the VIA. VIAs can sometimes damage this text on a seal screen, but I think it will be fine. Log footprint and double check here. Okay, see, the blue color is removed, so this is perfect. I love it. I really hope you love your PCB. Now we are going to change the width of the tracks, and I'm going to explain why. So when you search for this standard digital track impedance, you will find out they recommend 50 ohms. So if we go to JLC PCB impedance calculator, then for 50 ohms, here you can see impedance 50 ohms, calculate, and we are going to use this PCB stack up with this very thin prepreg, and then trace width for 50 ohms is 6.16 mil. So I'm going to find all 8 mil tracks, so these are all digital tracks, and we are going to change the width to 50 ohms to 6.16 mil. Oh, it's rounded 6.2 mil. It's fine, it's okay, we can use 6.2. So double check, okay? These are differential pairs, so these are 6.1. And these are the 50 ohm tracks, and they should be 6.2. 6.2, it means they are 50 ohm impedance tracks. Rebuild all the planes, and also rebuild all the polygons. So tools, copper manager, rebuild all. And we are going to double check the final PCB. I see, here is a connector or header is fitted, and I don't want to have it fitted, so just remove 3D model from this component and double check it. Perfect, the header is not there now. Before we send our board into production, we have to check if there are no errors. So in Schematic, run DRC check. Perfect. There are only the 2 warnings which are not really important. And also we need to run DRC check in PCB. So check DRC, No errors, no warnings. Perfect. Now, go to Export, Gerber Files, Export Gerber Files. This is the file what we created, and I'm going to copy it inside of this manufacturing directory. I'm going to create a temporary directory, and we are going to have a look what is inside of this file, what is inside of these Gerber files. And to view these files, what I usually use is viewer, which is called ViewMate. They have also a free version of the software. You can just download it, it's free. And then when you install it and run it, it looks like this. And I'm going to copy the path to the files from our project, and I'm going to import these files. So here are the Gerbers, and let's have a look what is inside. See? Click also on layer 14, and I'm going to import also the real files. So this is information about the holes on our PCB. I'm going to hide everything, and we are going to double check the layers one by one. So we can see the board outline, and we can see the top solder mask layer, top seal screen layer. You can enable combination of these layers and double check if everything is okay. Double check the text, especially you don't want to have mistakes in the text. This is the paste. Paste should be usually on the top of the paths. Combination with top layer. So this is the ground plane inside. These vias are very close to each other, but it's fine for this kind of PCB. Same here. Drill drawing. And this one is not really important. Okay, this is bottom solder. So this is the mask layer. Seal screen layer on the bottom. Paste. Mask and paste together. So you can see the logo doesn't have paste. That's good. That's how it should be. Okay, and this is the bottom layer. Drilling. So these are all the holes on our PCB. Everything looks okay. Perfect. So I can delete this. And we can use these Gerber files to manufacture our PCB. Next, I'll go to Export and Bill of Material. So this is the BOM. Be sure you have everything selected as I have it here. And also use same settings here. Export BOM. Here is the file what we just downloaded. I'm going to place it inside of manufacturing directory and open it. So in BOM, there is a list of all the components used on our board. These are on bottom layer. Here are the components, and we are going to double check if these unfitted are not listed. So this is the LED 102, and let's have a look. There is no LED 102, so perfect. And the last file what we need is pick and place. Again, be sure you are using exactly same settings what I have here. Export. And inside of this file there is position of every component on our PCB and rotation. See, this is how it looks. And what is very important, we may need to remove the components which are not fitted. So all the components which are on top layer, we need to remove them from the list. Otherwise, when we will be uploading this on on the website when we will be ordering PCB manufacturing, there will be warnings. We don't want to have warnings there. And also we would like to remove all the components which are not fitted, which are not in the BOM. So I'm going to select all these and I'm going to delete them from the list. Be careful, okay? Be sure you remove the correct components. And I'm going to save this as bottom assembly or pick and place. Okay, so this is the one what we will use when we will be ordering PCB. Go to JLC PCB website. Click here, instant quote. Now here we are going to upload the Gerber files. So inside of our manufacturing directory, I'm going to select the Gerber files. These are the files to manufacture the PCB. Okay, it looks good. And I'm going to change some settings. So we would like to use white PCB with ENIC. ENIC is the gold finish. We are using this stack up. Based on this stack up, we calculated the track width for 50 ohms. I don't want to have the mark on the PCB. And okay, so this is the price for the PCB itself. But I would like JLC also assemble the boards. I would like them to fit the components on the bottom side. And I would like them to ask me to confirm the component placement. And we can leave everything. We can just go to next. Now we are going to upload the bill of material. So again, from the manufacturing directory, I'm uploading the BOM file. And also we are going to upload the pick and place for the bottom components only. And let's have a look. Oh, they don't have two parts. Okay. So we will need to fit these manually. These are the ESD diodes and the RTC clock. But all the other components they have in stock, so they will solder all the components by themselves, and I will receive almost finished boards. So these are all the components which are going to be fitted. You can see the RTC is not fitted, the real-time clock. Also the ESD protection is not fitted. Okay, here we need to specify what kind of products is this. I think usually they use these for customs, so that's why you need to fill out something. Save to cart. And here it is. So this assembly process is quite expensive, but I'm doing this so everyone knows how to do it. If you think it is too expensive for you, you can buy the components by yourself and you can manually assemble the board. We can double check the Gerber files, what we uploaded, just to be sure everything is correct. This looks good, and you can also go through every single layer just to see. If everything is fine. Okay, I think it looks exactly the same as when we were checking these Gerber files. in the ViewMate. ViewMate is even a little bit better for checking these files because you can very easily combine the layers, and you can see the areas which are in both Gerber files. It's very, very useful. ViewMate is very, very useful. I use it a lot. Okay, I think this looks good. We can go back to this basket, and now I'm going to show you where you can download 3D models to finish the clock. Okay, so go to FEDEVEL GitHub called clock, and here are the files. Okay, so download all these files. This is the front panel for the clock. This is the thick one. This is the one what I would really recommend to use. There is also a thinner one, this one. It looks really cool, but the light is more nicer in the thicker panel because it spreads better. And this is stand. So there are two stands. One is for the thick panel, or for the clock with the thick front panel, and the other stand is for the clock with the thin front panel. Okay, so download all these files, and I'm going to manufacture all four. If you like, you can only manufacture the thick panel and the holder or stand for the clock with the thick panel. Remember the path. Go to this JLC PCB 3D printing, and this is how you order 3D printing from JLC. So click here, we would like to add 3D files. As I said, I'm going to add there all 4 files. And I'm going to manufacture these, not from this white one, but I would like to manufacture it from this black material. This is really nice material. I use it a lot. Okay, and maybe it's only $20, so maybe I would like to try also different material. So I'm going to upload all 4 again, and I will use different black material. So here I'm going to select this one, JLC black resin. Also here, here, and here. 35, it's fine. And also you need to put here description. Again, I think this is for customs, so you always need to put there something. I'm just going to call this clock panel. I'm going to copy this, and I'm going to place it also here. And here. And here. And we need to put description also for the stand or holder. So clock stand. Also here. This 3D printing is super cool. The quality is really good, and it's not very expensive. So I really recommend you to try it, not only for this project, also for your own other projects. Save to cart. Okay. Now we have here 3D prints, and these are all the 3D prints what we inserted into the cart, and here are all the items. We need to order these separately, so we need to order board separately and 3D printing separately. Or you can 3D print everything at home. So this is what I 3D printed. You can see the panel or two panels, the thick one and also the thin one, and here are also the stands or holders. So first I'm going to order these boards, 2 items, secure checkout, just continue, okay. And if there are coupons, you can use them. Okay, so I bought I ordered the PCBs. Now we have to do same for the 3D printing. So again, as I said, you don't have to order 3D printing. You can print it by yourself, 8 items. But it's not expensive and the quality is really, really good. And also they can do color 3D printing. That's beautiful. Submit order. We are not going to pay right now because they need to review the models first. So they will send us email. But as you can see, I also place order for 3D printing. I can close this. And here in order history, you can always double check the status. Perfect. Now, in the meantime, we are going to order the missing components. You remember they didn't have all the components. So the first one, I'm going to check which are the missing components. Here in bill of material, you can see which of them they don't have. So first the ESD protection. I'm going to find it in Mauser. You can use your own supplier, but I know they have them here, so I'm going to order. We need 4 for 1 board, so 20 for 5 boards. I usually buy a little bit more just in case, if it's not expensive. For expensive chips I buy exactly the amount I need, but for the cheap components I usually buy more. And also we need to buy the RTC clock. Do they have it? It's this one, okay. We are building 5 boards, so we are going to order 5 of them. Don't forget all the prices for PCB, what you've seen when we were ordering PCBs, they are for 5 boards. Okay, so it's not only for 1 board. And also we need the battery holder. So I'm going to try to find it. They don't have these, but I can try to search for battery holder. And I'm going to open datasheet. Oops. And double check the dimensions. So here I'm going to put 10 millimeters. Okay, this is exactly what we need. So 16.10, 16.10, 10.6, 10.6. Okay, yeah, that's exactly what we need. So we can buy some of these. And also don't forget to buy the batteries. Okay. FedEx, 20 euros. I'm going to order a few more things because then basically the shipping will be free. So if I don't add these few things, I would pay exactly same amount because I wouldn't have to pay for shipping. And I always wanted to try these boxes for SMD components. So I'm going to add this to the order. And still I need to add something a little bit more. Maybe I will put 2 here. Okay, shipping is 0 and I still pay almost exactly same money. But I have 3 boxes now and maybe I will use them. You will also need this film. So to create the display, we not only need the panel, we also need the film, and also you will need these screws, and maybe you would like to buy this right angle USB cable. And as I said, batteries, don't forget to buy batteries, but sometimes there is problem to ship batteries from different countries, so you may need to buy them from local shop. I'm going to put the list of everything what you need here into schematic, so it's easy for you to build the clock. Okay. Perfect. Save everything. Now, what I'm going to do, I'm going to create new version. So always when you send something to production, create version. So in case you need to go back to this specific version, you can always open it in EasyEDA. And that's what I always do. So I received the email from JLC PCB to confirm the placement. I'm going to double check on their website, action required, confirm parts placement. In 3D view, I'm going to double check this. So usually check the pin number 1, but they do it very well. Usually they do placement well, there should be no problems. So it's now submitted. Okay. They can start manufacturing. Perfect. And also I received the next email about the 3D printing. So they reviewed the models and now I need to pay for it. Everything is approved, so pay. Okay. Done. Let's wait what will happen. I received 3 boxes. Also in the first one there are the boards, in the second one 3D printed stuff, and also I received the box from Mauser with the missing components. Everything seems to be okay. So first, after you receive boards, double check quality of the soldering. You can see ESD protection is missing, LED is not fitted, double check pin 1 position, real-time clock is not fitted, the sensor is here, we will put it on the other side of the board. double check also if there is no short circuit between the pins. Okay, this looks good. On the other side, battery holder is not fitted. We need to do it by ourselves. No short circuit here. And everything else looks good. So we are going to solder down the ESD protection. First, I just put solder on the pads. Then I put a little bit more solder on one of the pads, so I can easily put their component. When soldering, use flux. Flux is very, very useful. Okay, then clean your board. This is how it looks when protection is soldered down. Now I'm going to move this away because I need space around the real-time clock. This is just temporary position for this capacitor. I will then put it back. Now add tin or solder on the RTC footprint. I also add solder on the RTC clock component. Put Kapton tape to protect the switches, then a little bit of flux. Be sure pin 1 is correctly located. That's the cut corner at the bottom, you could see it. Now place it on the footprint. And heat it up. You will very nicely see when it is soldered. And just to be sure, solder it manually. And then we can also put the capacitor back. Okay. Clean it and double check if everything is soldered properly. Looks nice. Now we are going to move the light sensor on top layer. So first desolder it. Remove the solder, put it from the top and solder it back. Be sure solder flows also on the other side of the board and put it a little bit up because the panel is very, very thick, so you can put it a little bit up. Now the battery holder. So first put a little bit of solder on the holder because it's very hard to solder it actually. So you can put it there. Do same for the pad. If you need, you can remove solder from the pad to make it nice and flat. Be sure you correctly place it. Okay, you can see where the back is and where is the front. Don't put it wrong way. It will be hard to desolder. And solder it down. Okay, clean everything. And also clean inside because you really need very, very good contact. So don't forget to clean it. Okay, we are going to do some measurements. So measure resistance both directions, so swap the probes between the ground and battery voltage. This is ground and 3.3 volts. This is ground and 5 volts. The board is not on, okay? We are just measuring the resistance, if there is no direct short circuit or something. Now I'm going to connect the power for very first time. Current is only 40 milliamps, so it looks good. And we are going to double check the voltage. So ground and 3.3 volts, perfect, and this is 5 volts, perfect. Mounting hole is connected to ground, okay, so that's why I use it for measurements. Here I'm going to measure the voltage. Okay, there is nothing, there should be nothing. I'm going to put the battery, but first I will disconnect the board. I'm going to take out the battery, place it in. Now measure the voltage. It should be 3.3 volt battery. Okay, perfect. And I'm going to connect the board and I will double check it again, just in case. Perfect. So these are two panels and I really like the left one. This one looks very nice. Clean it. Be sure you clean it properly, no dust, otherwise you will see the dust where the segments are. So clean it. Now cut out piece of the diffuser and stick it on the panel. Okay, and be sure it's nicely sticked. Cut the foil away. Now this is how it looks. Remove panel from the PCB. Put the PCB and the front panel together. Screw everything and it looks good. This is the right angle cable. Now go to FEDEVEL GitHub. There are all the files what you will need. Or you can just go on this URL, okay? Download everything. And these are the files, okay, what we downloaded. Inside of software, there is the file what we will need, but first, connect the clock, and when you connect it for the very first time, then you will see a drive. If I go here, this is the drive what you should see, okay? And copy this UF2 file, copy this to the drive. So this is the kind of like basic firmware. This is the Python interpreter. So this is not like the clock software yet, okay? This is just the firmware which will enable us to run Python. Okay, once it is uploaded, then you will see new drive, this one. And here we are going to copy all these files. So these are the clock related files. So this is the clock software and simply just copy it on the clock. So we need to overwrite the default code Python file. And now we have the software for the clock on our PCB. Disconnect power and connect it again. And now we should see something. Ah, we can see something cool. Let's have a look inside of this boot Python file. This is very important because there are some special settings which we will use a little bit later. Basically, this is saying that if we hold one of the buttons down, then something special will happen. Because right now you can see there is no drive. But later I will explain, okay, how you can update firmware. Right now I would like to open this HTML file, which we are going to use to configure our clock. So connect board. And first thing what I'm going to do, I'm going to switch on and switch off these dots. So right now they are not flashing, and now they are flashing. Can you see the dots are flashing now? By default they don't flash. Now, did you see what happened? Now the time is right. And I'm going to do something else. So this is the brightness, but it's quite low. So what I'm going to do, I'm going to increase the brightness. You can actually increase the brightness up to 1. That's very, very bright. I'm going to only increase this up to 0. I'm going to increase the brightness to 0.2. So now it looks good. Perfect. And this is how the clock looks. It's actually very hard to record it, so I had to create like special setup to be able to record the display. What I did, I created a couple of different modes, like timer mode, stopwatch mode. If you like, you can play with it, or you can also adjust the firmware. You can create your own software. I found the clock like super useful and fun to build. I use it all the time. I really hope you like this project. And don't forget, we also have the stand. Okay, so this is how it looks with the stand. I'm going to disconnect the clock. So one side of the stand is, or the sides, they have different angle. So you can use this one or you can use the other one, depends which one is better for you. Now, notice, as I said, there is no drive right now, but if you twice press reset button, then you are back at the beginning and you can actually upload the firmware UF2 file, or when you are connecting USB power and when you hold down this button, then you will be able to update the software for the clock. Notice now different drive is going to connect. This one, and basically that's the drive where are the files for the clock. And if you would like to use just the clock, only connect the power, and then there is no drive. That's everything what you need to know about the software support. Feel free to write your own and experiment and play with the clock. And that's everything for this video. I really hope you enjoyed designing this board and you build your own clock. I really hope you like it and you are going to use it every day. Leave comments. Let me know what you think about this tutorial and what I should build next. You know, what other tutorials or board designs you would like to see. And don't forget, if you would like to learn more about electronics and how to design boards, check out our online courses. You will find everything important there, from basic board design up to advanced board design and high-speed PCB layout. We have courses in Altium, Cadence, KiCad, and also courses covering many different topics, for example, FPGA, EMC measurements, and so on. Visit our website at fedevel.com. That's all for this video. Thank you very much for watching and don't forget to leave your comments. See you in the next video. Bye.